Justin was nominated for the Rose Award at Black Tie. Gotta be there to support him. Yeah, you have to be there to support him.
Can I share this? Ugh. Okay. Sorry, guys. All right. Bravo. Most of you did very well on the quiz. Let's go through this quick so that you have these concepts. I hope you saw also that I made a video of the bioequivalence and bioavailability quiz from last week, so you can check out the things that maybe you missed on the quiz to make sure that you're ready for mañana. It's a 90-minute test with 50 questions, so you need to keep moving. Most of them are fairly quick, but some of them aren't. So just keep moving. The topics are dosage regimen design, pharmacodynamics, bioavailability and bioequivalence, and volumes and protein binding. The equation sheet that you have is on, I forget where I put it now, but it's on the Canvas page. Okay, questions? You will have randomized seating when you come in here tomorrow. So unfortunately, can't be in your cozy little spot that makes you feel happy. Sorry. All right, ready? Okay, quiz on volumes and protein binding. A change in fraction unbound will always change the K and the half-life of a drug. Oopsie, oh brother. I don't want to rehearse. It is true. Well, let's think about this. What does fraction amount in tissue affect? VSS, right? And we know that changes in fraction unbound are going to change VSS, right? And VSS is a determinant of both K and half-life, right? So we could put in here this, couldn't we? And if there's a change in fraction unbound, there's going to be a change in half-life. If there's a change in fraction unbound, there's going to be a change in K, isn't there? Somebody thinks they got it right, but they didn't get it right, or you understood the concept, but picked something wrong, or could it automatically grades, so there, I don't know, I'll go look at it if you want me to, but Just send me an email, okay, and I'll look at it so that I don't forget. All right, the volume distribution of a drug has increased. What would you do to ensure that there is no change in the CSS average or peak to trough ratio? Again, what's volume distribution going to affect? Peak to trough, right? Won't affect VSS average. The dose rate should be what? Well, if the CSS average has remained the same, do we want to make a change in dose rate? I think hopefully you're all kind of in rote. Do I want to make a dose rate change? I look at CSS average, right? Has CSS average changed? No. Therefore, I do not want to change it. Dose interval, however, if there's an increase in volume distribution, what's going to happen to our peak to trough ratio? Well, an increase in volume of distribution is going to do what? It's going to make our K smaller, and it's going to make our half-life larger, right? They're inverses of each other, right? So if our half-life is longer and our K is smaller, we've got a change in our slope, right? That goes from here to here. So what's happening to our peak to trough ratio? Our peak to trough ratio has decreased, hasn't it? Now, most of the time that's fine clinically, but we could take advantage of that fact and extend our dosing interval, can't we? Give the drug less often. That'll be nice for our patient, won't it? So we're going to increase our tau. And remember, again, a good hint is if your half-life increases, you're going to want to increase your tau. If our half-life decreases, we're going to want to decrease our tau. You guys all good with that? So we are going to increase. Ready to move on? All right. Describe the relationship between VSS and fraction unbounded in plasma. Remember, we did fraction unbounded tissue in the workshop in here, but we haven't done fraction unbound in plasma. So hopefully you weren't tripped up by that. So here's our fraction unbounded plasma. Here's our volume of distribution at steady state. Which one is the dependent variable in this situation? VSS, that's right. VSS will be determined by, it is dependent upon what's going on with fraction unbounded plasma in this case, right? So the fraction unbounded plasma will go on our x-axis. Everybody good? Why is this so important? If we don't know what's determining what, we can get confused on what the results will be when we make changes. You have to know what is driving what. So in this case, a fraction unbounded plasma is driving the volume. The volume does not drive how the protein binding happens in the plasma, right? Are you good, Shamaka? You're looking, pardon me? No, well, next thing you do is figure that out, right? So we've got the independent variable on the x-axis is a fraction unbounded plasma. The dependent variable is VSS. Now, then the way I figure this out, I always say, okay, as the fraction unbound in plasma increases, what's going to happen to the volume? It's going to increase as well. So it's proportional, isn't it? Correct, right? Because it's on in the denominator here, right? It's the inverse. Okay. If it were FUT, it would be all the same answers. This would be FUT, this would be volume, but it would be inversely proportional because as the fraction unbound increases, the volume is going to decrease, isn't it? You good? Drugs where the fraction unbound in plasma is higher. So the fraction unbound is larger than the fraction unbound in tissues. Will have a larger volume of distribution at steady state. What'd you guys get for that one? Right, if this one is larger than this one, this is going to make this whole piece larger, and therefore your volume of distribution at steady state larger. What if I would have switched the wording around about something being bound more highly? Would you be able to twist it around and get where you need to be? Because remember, this is about fraction unbound. If I say that there was more, that the drug was more highly bound in the plasma than in the tissues, what's that going to tell you? There's less fraction unbound, right? And that, so it would be a smaller volume. So you have to be able to think all those different instances through and keep them straight, okay? You good? Ready to move on? All right, drug X is 15% bound to plasma proteins and 99% bound to tissue proteins. So it's only 15% bound to the plasma, but very highly bound to tissue. This means it's going to have a huge volume of distribution because it's stuck in that big compartment, right? If drug is displaced from its tissue binding sites by another drug, you would expect what? Okay, let's think about that. We have VSS is equal to VP plus VT, fraction unbound in plasma over fraction unbound in tissue. What does displaced from its tissue protein binding site mean? Another drug has come along and bounced off our drug, and now our drug is unbound, isn't it? So we're going to have an increase in fraction unbound in tissue, right, Eden? So we're going to see an increase in our fraction unbound in tissue, right? So what's going to happen to volume of distribution? If this increases, we can see that this is going to decrease, right? You all see that algebraically? If that denominator increases, that's going to take this whole thing down, and therefore our volume of distribution will be smaller. So therefore, it will a decrease in volume, right? What's a decrease in volume going to do to half-life? It's going to decrease it too, right? Half-life is equal to 0.693 volume over clearance. So if that volume decreases, so will the half-life, right? You good? You're looking at me with a little skepticism, but you're all right. Okay, good. We'll keep moving. All right, drug X. Another drug X is given to a patient for seizures and is under good control when a second drug Y is added that is also highly bound to albumin. So drug X is 85% bound to albumin, isn't it? Can you see that little number? It's 0.15. So it's very highly bound to albumin. The KD for drug X is 15.7 and the KD for drug Y is 5. So which of these drugs is going to be preferred by the albumin to bind? Drug Y, right? Why drug Y? It has a higher affinity, right? Why is that a higher affinity? The KD is low. Remember, KD is the concentration where half of the binding proteins are occupied. So the smaller the concentration, the higher the affinity, right? Just like KM, just like C50, just like all these Michaelis-Menten things, right? It's all just a riff on Michaelis-Menten. Do you see that? Do you see the beauty? The beauty of how they're all the same? KD, C50, KM, right? They're all just that concentration where half of whatever is full. So the smaller that number, the smaller the concentration needed to have half of the things full means it's more, has a higher affinity, more attraction, huh? So that smaller concentration of drug Y means drug Y has a higher affinity, which means drug X is going to be displaced from its plasma protein binding site, doesn't it? You see all that? Are you able to make all those inferences from the information? So at the end of the day, what's going on? We're going to have an increase in the fraction unbound in plasma of drug X, right? Everybody good with that? So what's gonna happen to bioavailability? Well, bioavailability, if you remember, is FA times FG times FH. Does it have anything to do with plasma protein binding? Hasn't even gotten to the plasma yet, right? Because bioavailability is a fraction of drug that makes it from administration to the systemic circulation. So no, it's gonna not change bioavailability. Remember, FA, FG, FH. So you think about what determines those, right? What about volume of distribution? Well, yeah, volume is all about where the drug is stuck, isn't it? Where it's bound. So if we have an increase in fraction unbound in the plasma, that's going to allow that drug then to move out into the tissues, and we'll have an increase in our volume of distribution. So this will increase, right? The volume will increase. Will the addition of drug Y require a dosing regimen change? Well, will we expect it to change our CSS average? No, because as far as we know, it hasn't changed bioavailability or clearance. What about dosing interval? Has the peak to trough ratio changed? Well, if the volume increases, it is going to change our peak to trough, right? An increase in volume, what's that going to do? Well, what does it do to K? Decreases the K. And increases half-life, which we know because those are inverses. We didn't even have to do that, right? And if there's a decrease in K, an increase in half-life, what can we do to our tau then? Increase it, that's right. Is this all a piece of cake? No. Getting better? All right, your patient weighs 95 kilograms and is taking drug A, which is 82% bound. So here's a bound question. So if it's 82% bound, what's its fraction unbound? (18.18), right? In the plasma, so the fraction unbound in the plasma is 0.18 and 25% bound in the tissue. So the fraction unbound in tissue is 0.75, right? What is the volume of distribution at steady state in liters? Well, VSS is equal to VP plus VT times fraction unbound in plasma over fraction unbound in tissue. What's the VP now? Unfortunately, I didn't give you 100 kilograms and I didn't give you 70. So 95 volume of plasma is 0.04 liters per kilogram times 95 kilograms. So those kilograms will cancel and we have some amount of liters. And this is given to you. Were you all able to find your equation sheet? Good. 0.56 liters per kilogram times 95 kilograms. And again, those kilograms will cancel and we have liters. .04 times 95 is 3.8. Is that what you got? (53.2). So this is going to be 3.8 plus 53.2. Fraction unbound in plasma is 0.18. Fraction unbound in tissue is 0.75. So with this being so much bigger than this is going to make this whole thing pretty small, isn't it? So now remember, you have to do the multiplication first, order of operations, right? 0.18 times 0.75 or divided by 0.75. I got 7.182 plus 3.8. Did I do that right? That's not. I got 16.568, and we're rounding to the 10th of a liter, so we're rounding to this number. So that's gonna make this 16.6. Is that right? Did I do that right? Good. Y'all can do that, right? That's just a plug and chug situation. It might be tricky if this is given to you in bound that you have to change it to fraction unbound, right? Your patient is getting 1,000 milligrams Q 24 hours of Doitree. This drug is highly bound to both plasma and tissue proteins. It's 95% bound to plasma. So the fraction unbound in plasma is 0.05, right? And 90% bound to tissue proteins. So this is 0.1. Does anybody have trouble making that translation? Okay. What would you expect if Doitree was displaced from its tissue protein binding sites, therefore increasing the fraction unbound in tissue? I was nice and gave that to you, wasn't I? So what's happening to volume? This is increasing, therefore volume is decreasing, isn't it? What would happen to VSS? It is going to decrease. Well, what dosing regimen changes would be warranted? Okay, so we are giving 1,000 milligrams every 24 hours. So our dose rate is what? If we wanted to know milligrams per day, this one's pretty easy, right? It's 1,000 milligrams per day, right? And our dose interval is 24 hours, right? So what's happening here? Our volume of distribution is decreasing. Therefore, what's happening with our CSS average? Anything? No, so we want to keep this 1,000 milligrams a day, don't we? What about our dose interval? Well, what's happened to our peak to trough ratio? Well, what's happened to K, clearance over volume? Our volume has decreased, therefore our K is going to increase, right? It's going to get steeper. Our peak to trough ratio is going to get larger, isn't it? And our half-life is going to get shorter, isn't it? Our half-life gets shorter, right? We're gonna need to chop this up into smaller birdie bites, aren't we? To get it more like a constant infusion, less variability in that peak to trough ratio. We wanna decrease this peak to trough ratio back to where it was. So instead of every 24, we're gonna go every 12 hours. So if we're gonna go every 12 hours, so we know this is 12. In order to keep giving 1,000 milligrams a day, what's our dose gonna be? 500. Does that make sense to everybody? You're giving 2 doses, 500 plus 500 is 1,000 in 1 day, right? You just divide that by 2. Drug Zoopolysil is a weak acid and it's in an acidic environment. If it's small enough, lipophilic, nonpolar, and has a concentration gradient, do you anticipate it will cross a membrane? Well, it has to be unionized, right? So really the question is this drug unionized? Is it preferentially in the unionized state in an acidic environment? So a weak acid in an acidic environment is going to be ionized over unionized, right? And we are in a low pH environment, so it's going to be favoring that unionized form. So is this going to favor passing through the membrane? Y'all able to think that through? We're going to be coming back to this when we get to renal clearance, so. Good. When comparing the factors determining protein binding from equation to the Michaelis-Menten factors below, which would indicate the analogous factor to each of the following. Well, remember Michaelis-Menten is the velocity of the reaction is the Vmax times concentration all over the Km plus the concentration, right? And you can see this is in the exact same form, isn't it? So our analogous values are these, aren't they? So the Michaelis-Menten constant Km, which is the concentration at half Vmax, is analogous to what? Kd, which is the concentration where you have half of your protein binding sites full. Is everybody okay with this? And it's a measure of what? Affinity, capacity, or concentration. Well, it's not, it is a concentration, but it's not the concentration of the system. That makes no sense. Is it a measure of affinity or capacity of the system? Does it tell you how much, in this case, proteins are available? Or does it tell you what the relative affinity is for the, between two drugs? It's the relative affinity, right? It's telling you the concentration where you have half of it. So these measures are always the affinity of the system, and these are always the capacity of the system, right? So Vmax, or the maximum velocity, is analogous to, and total, we already answered that, right? Which is the total number of protein sites available to be bound to. And it's a measure of what? The capacity of the system. Does that make sense to everybody? And if we look at, for example, our Emax model or our sigmoid Emax model, whichever, you see that that's also Michaelis-Menten, affinity capacity of the pharmacodynamic system, right? We're going to have more to add to it. So isn't that exciting? I tell you, with kinetics, you know a few things and then you can apply it. It makes you look so smart because you can apply the same principle over and over again, but you got to get that principle really solid in your brain and your ability to think through these problems. But once you have it, you know a lot. Okay? I hope you did well on this. And if you don't and you're still confused, please let me know because I will do whatever I can to get you there. You also have, we're having a review session at noon, and we have, and that's in 125. It will be recorded. Also, there are practice problems for you in final prep if you want to do some of those. That might be helpful to you too. All right, go back and look over your quizzes. There's a video for every quiz that goes through the quiz. See what you missed and make sure you've rectified that. Yeah. Can anybody, is anybody on their Canvas? You scroll all the way to the bottom. Is there a final prep folder in there? Do you see problems? And then there's a key for the odd or even problems. I don't remember which it is. Yes. Do you see it? Okay. So that has like, I don't know, 100 questions or something. Now it's through the whole semester for my questions. So you'll be able to tell when you get to where we haven't done yet. Yeah.
So on ExamSoft, some of our quizzes still don't have like the loaded frequency, like what we missed.
They've all been released. Has everybody else been able to get them? Nobody can get them. Oh my goodness, I'm so sorry.
Pharmacodynamics, some of the bioavailability ones are.
I released them all. I have to go in and see what I've done wrong. Yours, you got all 4 of them, all of them? Which ones?
The dosing regimen is out and then the one today.
And the one today. And the other 2 aren't. Okay, I'll go back and redo that. I'm so sorry. Thanks for speaking up. Let me know. I probably just screwed it up. So. All right, let's jump into the next topic, but this will not be on the exam. I want to give you an overview of clearance. We're not gonna have class on Wednesday, but I need you guys to spend some time watching some videos and getting your clearance concepts feeling solid, because we're gonna jump right in next week to hepatic clearance. Okay? When I get back. So, you're gonna have to do some work on your own, but you have that hour and you should be able to get through a lot of it in that hour, probably most of it. Okay. I gotta find it. Wait a minute, don't do that yet. So there's a section on clearance concepts. You don't have to do any of the workshop or any of, or any of the homework. If you want to, it might be helpful to you. Okay, is that up on me? No. Okay. All right. So we're going to talk about clearance concept, talk about elimination, which is made up of both. So once a drug is in the body, the first thing your body's trying to do is get it out, to be honest, right? So you absorb it or it becomes bioavailable. It moves around in the body, which is distribution, right? And now we're talking about getting rid of it. Well, how do we get rid of it? Well, there's two ways really, and sometimes both ways are used. These are the most common. That's not the only ways, but most of them are either the drug is metabolized or it's changed into something new, right? So there's some sort of chemical reaction where it's changed into a new drug that's called a metabolite, and that's called metabolism, or it's excreted out of the body somehow, usually by the kidneys, okay? So there's two major phases of metabolism that can occur, a phase 1 and a phase 2 reaction. Have you guys gone over this in 380? Metabolism at all? A little bit? No, not yet. Okay. So phase 1 is a little simpler situation. So remember we talk about in order for drugs to move through membranes and able to be absorbed, et cetera, it has to be unionized. It has to be lipophilic, right? But in order to get the drug out of the body, have you noticed that when you pee, there's not fat in your pee? There's no fat in there, is there? It's water, huh? Well, like fat, right? Like oil or something like that. Like they would rise to the, I don't know if you really study your pee, but it's aqueous, isn't it? It's water with some stuff in it. So how does a drug that's very lipophilic or lipid-like, fat-like, get out in the very aqueous situation of urine? It's a question you may not have pondered before, but now that you think about it, how would that work? It doesn't. The drug has to be in a more aqueous form to go out in the urine. So we go from the drug having to be nonpolar and lipophilic to it being polar and hydrophilic to get out of the body, right? So that's kind of a conundrum, which is why a lot of drugs are metabolized, right? They're changed into something that can be excreted in the urine. They're changed into something more polar. And so what that phase 1 reaction might do is stick a polar group on your drug and make it more polar, make it able to be eliminated by the kidneys. Does that make sense? So a lot of metabolism is just trying to get that drug out of the body. Okay, and phase 1s are pretty simple. You know, it puts on a polar group, it sticks a hydrogen on, it's very simple reactions. Whereas phase 2 are conjugation, where there's all the acetylation, all the fancy stuff that happens are phase 2s. And again, a polar group is added. it'll be catalyzed by a specific enzyme, but the P450 system are all phase 1 reactions. They're simple reactions. Where can drugs be metabolized? Well, the liver is the biggest spot. We also know that the GI wall metabolizes drug because there's enzymes in there, right? We've already talked about that. In order to get through that gut wall, you have to make it through the enzymes and the P-glycoprotein. And remember, one of those are enzymes, which means the drug is metabolized if it interacts with that enzyme. There's also metabolic tissue in the kidneys, skin, lung, and in the blood itself. But the major metabolic site is the liver, and then also in the GI wall. Excretion, most drugs have to be altered before they can be eliminated. Why? Because they have to be lipophilic enough to move around in the body and get absorbed. Now, there are some drugs that we give IV because they're very polar, and therefore they wouldn't get absorbed or they wouldn't get to be able to move around in the body. But we give them IV because they're very water-like, they're very polar. Those are going to go right out in the kidneys without needing any type of metabolism, right? What are the excretion sites? Well, we know kidneys are the big ones. We also can have drugs breathed out, right? You also can sweat drugs out. But the big one is the kidney, isn't it? So what I don't want you to think is if it's metabolized in the liver and we talk about liver clearance, that it's somehow that molecule is flying out of the body. No, there's no elimination from the liver, but what does the liver do? Changes it into something new. So it's no longer that drug anymore. It's a new drug, isn't it? That metabolite. So that's why that first drug that's given is considered gone. It's now a new drug. Does that make sense? But the molecule itself is still in the body. I had people for a long time thinking that things flew out of the liver, but there's no way out directly from the liver, is there? So why do we care about clearance? Well, what is clearance, first of all? Clearance is a little tough because clearance is, at least for me it was, because I think we get it so easily mixed up with elimination rate constant. Clearance is not how long it takes to get out of the body. That's elimination rate constant or half-life, right? That's K and half-life. What's clearance then? Clearance is really how effective or efficient, I'll read you the definition in a minute, but it's really the efficacy and how efficient the body is at getting rid of the drug. And the definition of clearance is the amount of blood that can be have all the drug eliminated from it per time. So the units are volume per time. The units are always volume per time, which to me is not necessarily, does it make sense to your brain, especially if you're thinking of, is it a rate? It is not a rate. It's a volume per time. So it's actually a flow, isn't it? How much of that blood that flows by can have all the drug taken out of it per time? So how efficient or effective is that drug? The units are always in volume per time. If you come up with amount per time, that's not a clearance. Okay. Why is clearance important? But when we first learned about dosing regimen design, we think about, do we want to change our dose rate? Well, that depends on CSS average. What determines CSS average? Drug in over drug out, right? Oh, clearance is what determines drug out. So clearance will affect dose rate, won't it? And CSS average. What about dose interval? What determines dose interval? Well, peak to trough ratio, 1, right? Which is 1 over e to the negative k tau. We control the tau, but k is determined by, clearance. So unlike bioavailability, which affects dose rate, but not dose interval. And unlike volume that affects dose interval, but not dose rate, clearance affects both, doesn't it? Clearance affects both. Oops, sorry, amount of blood that we can have. It's always volume per time. All right. What determines clearance? So, do these things determine clearance? Does CSS average determine clearance? So if our CSS average is 10 and it goes to 20, does that determine clearance? Clearance must go down then, is that right? Or go up? I don't remember what I said now. Is that right? No, because that is not the dependent variable, is it? This is why you have to understand, what's the dependent variable? CSS average is dependent. So these things don't determine clearance, do they? Nope. How about these? Do volume and K determine clearance? So if clearance increases, that must mean that, or I'm sorry, if volume of distribution increases, that must mean clearance has to increase. No, 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 no. If volume increases, that means K's changed, right? So again, this is not arranged correctly. It's K is equal to clearance divided by volume, right? You can use this to determine these, but the dependent variable is here. That's the same thing here. Dependent variable is here. So no, clearance is not determined by volume and K. What about this one? These are all ways we can calculate clearance, but do these determine clearance? Does the dose IV and area of the curve determine clearance? No, I'm not going to fool you this time, Shamaka, am I? Which is the dependent variable here? The area of the curve. So no, none of these things don't determine clearance, but if that's the case, then what does? Well, let's talk about that. Here's our clearance model. Isn't this exciting? Here's our clearance model. What are the determinants of clearance? Well, we have blood coming in with a certain concentration. So this is your arterial concentration coming in, and Q is blood flow. So how fast? So we have blood coming in with a concentration of Ca. Then it comes into the clearance organ, and then the blood comes out at the same rate, right? We still have the same blood flow coming out, but now it has a concentration of venous, a venous concentration. So Ca is going to be greater than or equal to Cv, right? If it's equal, then it means no drug was eliminated, right? This assumes no irreversible binding of the drug to the organ. This applies for any clearance organ, but we're gonna think about this as the liver. Want to think about drug coming into the liver at a certain rate with a certain concentration going out, and any drug that's eliminated is eliminated. And I'm not going to go through all of this, but you guys can see how we derive the rate of extraction from the rate of input. So the extraction efficiency, what is the extraction efficiency of a drug by an organ when the concentration coming in is 100 and the concentration coming out is 100? Well, how do we figure the concentration? So the concentration is concentration in minus concentration out all over your initial concentration. So your concentration in this case is 100. Your concentration out is 100. So was there any drug removed? No, right? So your extraction efficiency in this case is 0, isn't it? What if what is the E of a drug by an organ when 100 milligrams per liter comes in and 0 goes out? So 100 comes in minus what goes out all over what we started with. And that's gonna be 1 or 100%, right? All of it's removed. So here, the E is 1 or 100%. So your extraction efficiency is going to be between 0 and 1. 1 means all of it's removed. 0 means none of it's removed. So this last one, if 100 comes in and 25 goes out, what's the extraction efficiency gonna be? 100 minus 25 all over 100. 0.75, right? Oops. Oops. Yeah, there it is, 0.75. You all good with that? All right, I'm gonna stop there because this gets into some tricky stuff that we'll pick up on when we get back. So try to make it through the rest of these slides on clearance concepts, and then we'll be able to go pretty quickly through hepatic clearance. But don't worry about that till you're done with your exam. Well, I'll see whoever wants to attend. Remember, I won't have anything planned for your review session, but I will be there. 125. Thanks so much.